Well, thank you very much. So I'm a senior developer at Microsoft working on Vcpkg for the past 6 years. And today I'm going to talk about actually some kind of up and coming actively developed features of Vcpkg. These aren't fully GA yet. They aren't fully production ready, let's say, but it's kind of a preview of what we're doing that's kind of new and interesting in the package manager. Some improvements that we're making, especially around the area of supply side security, which is, as we all know, very, very important right now. So first of all, what is Vcpkg? So Vcpkg is the open source first-party C++ package manager by Microsoft for all developers on all platforms. So this is not a Windows specific, but of course it does cover Windows as well as Mac, Linux, and any other system that you would target with C++. This includes mobile operating systems, other compilers, WASM, and more. Currently, we have about 1,800 libraries with tens of thousands of versions available in our centrally curated set that we regularly test. So C++ package manager builds from source. So today, the questions I want to cover that I hope you'll walk away with an answer to is, first of all, what do we consider an asset in the framework of building C++ packages? Second is, what problems do you encounter when you want to manage assets? Third is, what's the most extreme case? Can we come up with some sort of ideal scenario that if we solve this, we think we have a good solution for the general question? What is Vcpkg's solution to this extreme case? And then how could you use Vcpkg in your enterprise, in your environment, in your situation, in order to solve all of these problems? So first of all, what is an asset? So for Vcpkg, what we consider to be assets are basically static content that we can fetch. So this can be source code most of the time, but this also includes other tools that might be needed during the build process. For example, YASM, so the yet another assembler, that would be a tool, or Bison and Flex, or Perl, or if we need to download Python in order to interpret Scon's build scripts, or the Meson build system. All of these are tools that we might download on demand as necessary to build a particular package. And then finally, sometimes we even download patches as separate files because, for example, maybe in order to solve a compatibility problem, we need to fetch a patch from a Git commit that is not yet on the main source code branch. So we have a bunch of different static assets that we already know the content of we want to fetch. But along the way, of course, there's all kinds of problems that can happen when you're fetching things over the internet. Obviously, the remote server that we're fetching from could be compromised. The assets could be moved out from underneath us. Even if the remote server is good, and even if your machine is good, there's always the chance that somewhere in the middle in your network, you have some sort of interception. Ideally, we try to use HTTPS as much as possible, but sometimes things are not available over HTTPS, in which case we have to use HTTP, and man in the middle becomes a very real threat. Unfortunately, there's the possibility of either authors that don't necessarily have aligned intentions with the user, or even somewhat outright hostile situations where an author might say, well, you know what, I don't want you to use this version anymore, so I'm just going to take it down, right? I'm just going to take it off my server, and you can't get to it anymore. And so how do you, as a project, as a business where you want to rely on things, how can you rely on something that can just be removed, ripped out from underneath you any day? And then finally, of course, is the network is reliable. Fallacy number one of distributed computing. Just because you can fetch it today and just because the author wants you to be able to fetch it doesn't necessarily mean that the hardware that minute is going to transmit your packets there and back. So we got a bunch of problems. The ideal case that kind of is the distillation of all of this is that your system shouldn't depend on the public internet. You should be able to build all of your dependencies. You should be able to build your product start to finish without necessarily needing the public internet. Now, it can be very convenient to have the public internet available as backup, and it's I think it's much rarer that a business would actually choose to go all the way to the origin of the name air gap, meaning your network is physically disconnected from the outer network, but you can have kind of virtually air-gapped systems with firewalls in place. So this is kind of our target and the name of the talk of what we're looking to solve problems for, is in the context of an air-gapped system, somewhere where the machine doing the builds is not cannot directly access the public internet. So obviously this poses a bunch of complications even further, right? So one obvious way would be that, well, we'll just take every build system, every recipe, we'll take every URL and we can rewrite them, right? That technically works, but that completely defeats the point of open source, right? Open source is about sharing. It's about reuse. It's about one person solving a problem and it benefiting everyone. Um, and so clearly, if everyone has to rewrite everything to work in their internal network, that really isn't open source anymore, right? It defeats the whole the virtues. Um, there are One could imagine trying to do something like faking out the internet, and that could work. But reverse proxies are notoriously difficult to actually set up and maintain. And even if you did have a reverse proxy, you start running into problems if maybe the same URL accessed in different ways has different results, and that can get very, very complicated. So for Vcpkg, we, from the very beginning, for exactly these security reasons, we insist that every one of these statically downloaded assets, we have a pinned SHA-512 hash of the asset itself. We don't rely on signatures to validate the authenticity. Rather, it is pinned directly. The exact content is pinned, so it is not allowed to change, even if the signature would match. If the content is different, it is not accepted. So because we know the SHA-512 hash of every asset that we want to download, well, that's a key, right? That's a key into a map. And so our solution for this problem is that you simply need to have a system that, when asked for the hash, it can return that object. And it's very straightforward to transfer objects from the outside to the inside. It's very simple to validate objects because you are accessing them by the hash. So you simply just hash the results. So it lets you separate the problem of kind of authenticity and integrity. So we're very easily able to solve integrity via using hashes. And you may not know it, but you probably use a system based on this concept every single day, and that's Git. So Git uses SHA-1 hashes of files and of data structures as its fundamental implementation. A Git commit is really just a hash, a SHA-1 hash of the commit information and the SHA-1 hash of the file tree, like the snapshot of the files under management. So this is technology you're already familiar with, just being exposed. So in Vcpkg, we're planning to ship 2 initial implementations. We have a very simple HTTP-based implementation of this that can stand up on top of any web server that accepts GET and PUSH, which includes, for example, Azure Storage. So Azure Storage, Blob Storage supports GET and PUT directly as access mechanisms. So you can stand it up directly on that if you're looking for a turnkey solution. But you could also set it up on top of any sort of private Apache or IIS or Nginx instance. And then there's that's the simple, super easy to set up. And then, of course, the cases where you might want something more complex. For example, you might want to use a different protocol. You might not want to use HTTP. You might use gRPC to access the cache, or you might need to tickle several web services, or you want to consult them in a certain arrangement, or you only want to redirect some calls. All of these, we have a very simple and easily extensible way to build it out for your particular network. So you only have to worry about your infrastructure's concerns, and Vcpkg will take care of making sure every recipe works with your system. So in Vcpkg, a given recipe looks like a script. Technically, they're written in the CMake scripting language, but that's really that's really an irrelevant detail here. The point is, it looks like an imperative script, and so there will be a series of file descriptions that boil down to something like this: Vcpkg download dist file into the variable name output variable, and then it'll have a list of URLs such as mirrors where the file can be found, a local file name to save the file as, and then it'll have a SHA-512 of what that content is expected to be. And Vcpkg, of course, will error out if the content doesn't match the SHA. Then in the simple HTTP case, we would take this SHA, we would take this URL, and the recipe actually invokes the Vcpkg tool again. And this is that layer of of abstraction. It's the broker that allows all recipes, no matter whether they're accessing it from any different way. It allows all of those to be redirected through Vcpkg, which then you can customize and configure for your particular situation. So this is an example of the simple HTTP case against Azure Storage. You can see here it does a GET request against the storage. Maybe the storage returns the result, maybe it doesn't. In the case that it doesn't, Vcpkg can be configured to automatically fall back to fetching it from the internet and then storing it to your storage cache. So this is completely automatically managed. You don't need to set up any services in order to have this work. Vcpkg, the client, will automatically manage caching the files into your storage account for you, just transparently under the hood. This system exactly is what we use for our curated CI system, where we build these 1,600 packages we build them all every night, as well as on every commit, we build the cone of destruction. So all of this is backed by exactly what you're seeing on screen right here with this simple HTTP caching system. Now, as I said, though, sometimes that won't work for more complicated networks, such as inside of Microsoft. We can't necessarily use this system always. So in a more complicated case, Vcpkg simply is able to relay all of these details in a very systematic way to a user-provided executable or script. So you can write using whatever your company's infrastructure language is. If you prefer Python, you can write it in Python, C#, PowerShell, Bash, you name it. We're doing a shell call, so you can implement this in the most maintainable way for you and your teams. Then, of course, that script goes off and does whatever it needs to do. Performs a gRPC call, performs some HTTP calls. It might hit your internal cache service, which then maybe if you are, a microservice kind of, I guess Web 2.0 is a little outdated at this point, but, a kind of a web-first microservice organization, you might set up a cache service like this that then can contact the internet on behalf of the script, so that the cache service will do the caching, and you're guaranteed from like construction that all accesses shall be served from the cache. And in fact, something very, very similar to this is what we're implementing right now inside of Microsoft for some internal purposes, and I hope we'll be able to ship that publicly in the near future. So as I mentioned at the beginning, this is an actively developed topic. We have open PRs. It's experimental, but we're really excited about the possibilities that this brings for enterprises who have much stricter security constraints, such as I mentioned, the kind of air-gapped, maybe doing government work. And we're really excited about the potential to leverage open source without modifications in a private network. So you can use these build definitions, from the community that have had so many man hours put into them. You can reuse those within your custom infrastructure as is. We do have some open questions that we still are working on. So for example, we have about 1%, less than 1% of our packages actually can't be fetched via HTTP, and therefore they can't necessarily be mirrored in this way. For example, I believe it is Google Code. So Google Code, the host, only serves files reliably over Git. If you try to download a zip of the sources, they change every time you access because they encode the date. So there's no way to get like a bit stable copy. Now, there are some options for Git. We've found that there are some settings for Git to potentially redirect things. And so that's something we're investigating on exactly how to solve this. However, for most users, we don't think this is an issue. This affects only a very small number of packages. I've only described 2 systems here, but I think given the structure, you can imagine a bunch of other configurations that would be super useful out of the box. Maybe if we could make it easier to set up that microservice in the more complex script example, we could build some sample scripts into the tool. And so we're going to look at how we can expand that and make it easier to use in the future. And then finally is distinguishing between private and public assets. So if you're only using Vcpkg for like open source packages, then all of this just works exactly unmodified. However, if you're mixing private packages with public packages, you might only want to cache the assets for some of them. You might not want to cache your corporate source code into this asset service because you have your own code servers and you really prefer to fetch that all the time. So right now, of course, that's doable with an external helper that could just simply look at the URL and say, oh, well, if it's an internal URL, I don't need to cache it. But of course, that's more complicated than it really needs to be, and we're looking at easier ways to implement that. So this is kind of our roadmap around some new things we're doing in supply side security. This isn't necessarily the solution for all package managers, but it meets the needs of how Vcpkg specifically works in the way that the rest of our systems are configured. So, finally, try out Vcpkg. If you work in C and C++, I'd love to hear from you about either how Vcpkg works for you or doesn't work for you, or what features you need. We've been pushing out an incredible amount of new features that have been requested by the community recently. We have full support for private registries, versioning. We have a manifest file that you can declare, a JSON file. You can list out your dependencies, so that way when you build in one place and you build in another place, you get exactly the same results. And caching, of course, caching builds and reusing them across multiple machines to save you CI time and improve your developer workflow. So on screen, I have the URLs for the project from GitHub, as well as vcpkg.io, our website, and then vcpkg@microsoft.com is the email where you can contact myself and my team for any questions you might have about Vcpkg. And with that, I'd be happy to take any questions. Oh, Pradyun, I think you're muted.
I am. It doesn't let me put you as the highlight, which is sad. Well, I don't see any questions so far. I guess we'll wait for a moment here, since looking at the past few talks, there's a few questions the moment we're done. So
yeah, and I'd be happy to answer any questions about Vcpkg or otherwise. And I want to reiterate that this is not necessarily the only way to solve this problem, but this is just what works best with kind of how Vcpkg works. And I don't want to get too much into the ways that other systems solve their problems. I wouldn't want to speak for them, but